Alright, question number 8 on the final review. This is talking about rotational dynamics, and it's talking about a hoop. It's released from rest at an incline with a height, and you're supposed to find the speed at the bottom. So anytime you see a problem like this, and it's talking about hoops rolling down ramps or up ramps, whatever, it's always conservation of energy. And that says that the energy initial is equal to the energy final in all cases. Now the energy initial and the energy final can be made up of different types of energy. So initially you can have gravitational potential, elastic potential, rotational kinetic, and translational kinetic. There's also different kinds, but that's all we worry about right now. So all of those would be present in the initial case, and then you have the same forms, gravitational potential, elastic potential, translational kinetic, and rotational kinetic present in the final case as well. Now, they don't all have to be there every problem. So what you do is usually look at your situation and cross off what you don't have. Now, in this problem, it starts at a height, so that means we have gravitational potential. We don't have any springs, so no elastic potential. Initially, it's at rest, so that means it's not translationally moving or rotationally, so lop those off. And then at the end, it's at the bottom of the incline, which means it's at a height of 0, so no gravitational potential. There's no springs, so no elastic potential, but it is moving, so we have the kinetic energies. That gives us a relationship of gravitational potential equal to translational kinetic plus rotational kinetic. Formula for gravitational potential is mgh. Translational kinetic is 1/2 mv squared, and rotational kinetic is 1/2 I omega squared. So you end up at that problem. We don't know the formula for inertia at this case, and we don't have the angular speed. So what you can do is rewrite the formula for rotational kinetic in terms of values that you already know. Now we're talking about a hoop, so a hoop has an inertia formula of mr squared, and then omega is velocity divided by radius squared as well. So you can go through and solve and distribute. You get mgh is equal to 1/2 mv squared plus 1/2 mr squared v squared divided by r squared. So there's a lot of things going on here. But since you have an r squared on the top and the bottom, we are able to get rid of it on both spots. So you end up with mgh is equal to 1/2 mv squared plus 1/2 mv squared. Now for a hoop, this is always true when you have a relationship like this. If it starts from rest at a height and rolls down a ramp, this formula is always going to be the one that you use. So mgh is equal to 1/2 mv squared plus 1/2 mv squared, which is just 1 mv squared. You have an m on both sides of the equation, so you can chop it off. So you end up with a formula that's gh equal to v squared, which can be rearranged to solve for velocity as the square root of gh. Now we have gravity and we have the height, so that's how we're going to solve problems like this every time. It's the easiest thing to plug in, so we want to get it down to the easy formula that we have right in front of us of velocity square root gh. We end up with a speed 3.16 meters per second. So again, just to make sure, the formula for a hoop for inertia is mr squared. That's where that came from, and that's why we plug that in. So discs and spheres and cylinders and all that jazz have different formulas, so make sure that you're comfortable with those.